So uniform circular motion is going to be studied in two different aspects, from kinematics point of view and from dynamics point of view. And it's just another type of motion. So far we've talked about kinematics in 1D, in one dimension, uniform accelerated motion, uniform motion. Then we dealt with motion in two dimensions, especially projectile motion. In grade 11, we dealt with wave motion and simple harmonic motion. And now we're just adding one more, uniform circular motion. The key word here is uniform. So it's a motion in a circle with constant radius and constant speed. So remember, it's constant speed, not constant velocity. Keep in mind that the velocity is always tangent to the circle, to the path that the object is going through. It's changing the direction, but not magnitude. So in this case, even though I have v1 and v2, there are two different vectors. However, the magnitude of v1 is the same as the magnitude of v2. That's what it means, constant speed. So we're just going to call it v, right? So that's what constant speed means. All right, so let's quickly deal with the kinematics of uniform circular motion. Okay, so usually we do a trick here to verify this equation. Okay, so it's radial or centripetal acceleration is v squared over r. All right, that's our first equation in uniform circular motion. The way how it's derived in here is pretty straightforward. We're using calculus. It's somewhat more clear. However, here we're going to use similar triangles. So we have two triangles here. One, we have this, the actual portion of the path that the object is going through. And then this is the difference between the two velocities, right? So the two triangles that I shaded, they are similar triangles, okay? So we use similar triangles. And what we do here is we say, well, delta V over either V1 or V2, the magnitude, but V, so the ratio of sides is the same, right? So delta L, which is this side here on the triangle, which is pretty much almost the path, over R, right? And what we do here is we do some tricks. So we divide both sides by delta T, by the time it took the object to go from point A to point B. So very simple, delta V over V times delta T is equal to delta L over R times delta T. And then we look at this two ratios, V over delta T here and delta L over delta T. So delta V over delta T is nothing but acceleration according to the definition of the acceleration. And delta L over delta T is nothing but the speed of the object, right? We're making an assumption here is that our path is almost delta L, right? That straight line, because the angle is this delta theta is very tiny, all right? It's going towards zero. So once I've done that, sorry, we're using red here. So once we've done that, this is 3, then we rearrange. Pretty much we have A over, and this is centripetal acceleration, is what keeps an object in a circular motion. So AC over V is equal to V over R, or AC is V squared over R. So this is with regard to the magnitude. One thing that we have to remember is that this is a magnitude. So let's write it here. Magnitude of acceleration is AC V squared over R. You can do the unit analysis. You will get meters per second squared. Direction is AC is always perpendicular to the instantaneous velocity at that point. All right, so these are the two characteristics of centripetal acceleration that we ought to remember for uniform circular motion. Some other, before we go, or actually we can go to kinematics. So of course, in order for an object to have an acceleration, there must be some unbalanced force, right? And remember that the force, the net force, is parallel to the acceleration, right? So which means that Newton's second law, so which means that the net force has to point toward the center, all right? And now we can write Newton's second law for this uniform circular motion, that is F net equal to mass times acceleration, or F net equal to mass times this v squared over r, since the acceleration is this centripetal acceleration. And the net force on a uniform circular motion, we call it centripetal force, so we use Fc equal to m v squared over r. And this is Newton's second law for uniform circular motion that we'll use in our course. Some other kinematics quantities. All right, so since we're dealing with periodic motion, in periodic motion, we like to know about period, which is the time to complete one cycle, right? It's measured in seconds, and frequency, which is revolutions per unit of time, right? Cycles per unit of time, which is measured in hertz, right? From grade 11, if you remember, frequency is 1 over period, right? So that's one equation. And now we start dealing a little bit, since we have a circular motion. So we try to relate now all the quantities together. On a circular motion, the speed of an object going on a cycle is going to be the length of the circle, so the perimeter, divided by time, right? Divided by a period. So there is another equation that we will use. Or the velocity is 2 pi r times frequency, right? That's another relation, since frequency and period are the reciprocal of each other. Okay, therefore, if I were to find out the acceleration in terms of, so recall this v squared over r in terms of period or frequency, instead of v, I'm going to write 2 pi r over t squared over r. And if I expand, I get 4 pi squared r over period squared, or 4 pi squared r times frequency. All right, so this is another manipulated relationship that you might want to keep it handy when you're solving uniform circular motion questions. So these were the main concepts that we need to know, and formulas related to those concepts for dynamics in grade 12. Our next natural step is to solve some problems. So before we go into solving problems, here are the steps that we're going to use always. And they are standard, as you notice, even in the first unit. We read the problem, we read it again, we draw a sketch. Now what is a new thing here? We draw a free body diagram, all right? We choose a convenient coordinate system. Remember, we choose the x-axis and direction of the acceleration, if that is known, all right? We list the given and required quantities. We find what relationship is between them. And for that, we use, remember, from now, we use either Newton's laws or kinematics or both. And in a lot of questions, we're actually going to use both of them. We rearrange the equations, we come up with a solution. In terms of variables, we do a quick estimation to see whether it's correct. All right, so we did solve algebraically, then we were happy, we put the numbers, we keep track of dimensions, so we make sure that units are correct. And then we make sure our answer is reasonable, so not something that doesn't match our expectation for that particular problem, and then we report the answer. Okay, so we have the tools, we have the algorithm to solve the problem. Now it's time to solve problems.